Students, now we are going to discuss about monosaccharides. As you know, these are also known as simple sugars. Also known as simple sugars. It consists of single aldose or ketose, which cannot be hydrolyzed further. Okay, students, into more simple sugars. Got it? Okay. Now, if you see the examples of it, it includes glucose, fructose, mannose, galactose, and your ribose. They are usually represented as CN, H2O, N. For a for a carbohydrate to obey this rule, it should minimum require 3 carbons in it. Okay, how many carbons it require? Minimum 3 carbons. So, what is the 3 carbon monosaccharide which has aldehyde group in it, students? Yes, it is your glyceraldehyde. And what is that similar thing which has keto group in it? Keto group, it is your glyceraldehyde. You have aldehyde, it is dihydroxy acetone. Okay, let us see the structure of glyceraldehyde and your dihydroxy acetone. If we draw it, it will be having 3 carbons in it. It also has 3 carbons in it. It has an glyceraldehyde has aldehyde group which is represented like this. In the first position, and dihydroxyacetone has keto group in it. In the second position, okay, this is the structure of glyceraldehyde and this is the structure of dihydroxyacetone. Acetone. Okay, very good. Now we will see the classification of carbohydrate monosaccharides. How is this classification of monosaccharides made? It is based on the functional group and based on number of carbons present in it. Group and number of carbons, number of carbon atoms. Okay, now Based on the functional group, we have one is your aldehyde and another thing is your ketone. Now, if a monosaccharide has three carbons in it, they are called as trioses. Very good. Three carbon. What is that three carbon triose in aldehyde? It is glyceraldehyde. What is that three carbon triose in keto group? Yes, it is your dihydroxy acetone. Okay. Four carbon thing is called tetrose. What is that aldehyde in tetrose? Yes, erythrose. And the ketone group? Erythrulose. And 5 carbon pentoses. Aldehyde, it is ribose and xylose. And ketoside, it is ribulose and xylulose. 6 carbon, as you know, they are called as hexoses. The aldehyde, yeah, you know it, glucose, mannose, galactose, and in the keto, it is fructose. Okay, very good. Now 7 carbon, it is heptose. In keto group, it is pseudo heptulose, which you see in your HMB pathway. Okay. Now we will see, before seeing the properties of monosaccharides, we will see the isomerism in monosaccharides. Isomerism. What are isomers, students? These are substances or compounds having similar molecular formula but with different structures. So these are substances or compounds having, they have same molecular formula, but if you see their structure, they will be different. Okay. And now we will see the classification of isomerism. Isomers, isomerism in carbohydrates, particularly monosaccharides. It is of two types. One is your functional isomers or constitutional isomers, and another thing is stereoisomerism. Okay, this functional isomers is based on the different functional group present in it. Of course, we will see it deeply, like for example, glucose and fructose. And in the stereoisomerism is because of the change in their spatial arrangement, difference in their spatial arrangement. Okay, in stereoisomerism, again we have enantiomers and diastereomers Okay, even and in diastereomers we have epimers and anomers. And there is another type of isomerism called optical isomers. Few textbooks they had given optical isomerism under stereoisomers and few in a separate way. Okay, these enantiomers are based on the penultimate carbon, and dine and enantiomers are mirror images, and diastereomers are not mirror images. Then anomers are cyclic compounds, and we will see it briefly now. Why there is isomerism in carbohydrates? It is presence of chiral carbon. Isomers are formed due to the presence of chiral carbon. What is this chiral carbon, students? It is a carbon which is surrounded by three different atoms or molecules, or which is surrounded by different molecules or atoms. It is called as chiral carbon. So if you see, write a note: dihydroxy acetone cannot form isomerism. What is the reason, students? Reason is it does not have chiral carbon. Okay, got it? Okay. Now we will see different isomerisms one by one. One is your functional isomers. What is the other name for these students? Okay, constitutional isomers. No, they have same molecular formula, but what is different here? With different functional groups. Okay, now these, for conversion of one functional isomerism into another functional isomers, the enzymes are isomerases. Okay, note down: reversible interconversion is by the help of enzymes isomerases. Okay, got it, students? For example, glucose and fructose. Like during your glycolysis, glucose 6 phosphate is getting converted into fructose 6 phosphate with the help of enzyme phosphohexose isomerase. In the same way, your ribose will be reversibly interconvertible into ribulose, and xylose getting interconvertible into xylulose. All these three require isomerases as enzymes. Okay, now we'll go with stereoisomerism. So As you know, in all the isomers, it is same molecular formula. In stereoisomerism, they have same functional group also. Functional group, but atoms differ in their, we had already discussed what are atoms differ in their, yes, spatial arrangements. Spatial arrangements around one or multiple carbons. What are these stereoisomers, students? These are isomers which have same functional group but atoms differ in their spatial arrangements around one or multiple carbons. Okay. Now, in order for a compound with n number of chiral carbons, chiral carbons, how many number of stereoisomers it can be? It will be represented as 2 power n. Okay. If a compound has n number of chiral carbons, 2n, 2 power n stereoisomers are possible. So, if you take the example, glyceraldehyde has how many chiral carbons, students? Yes, glyceraldehyde has one compound, chiral carbon. So, how many stereoisomerism isomers are possible? Okay, only 2 power 1. It is two stereoisomers are possible. Okay. Now we'll discuss about enantiomers. Enantiomers are stereoisomers. These are stereoisomers. These are stereoisomers which are non-superimposable and mirror images. The best example is your hand, students. See, both the hands are appearing similar. They are mirror images to each other, but they are non-superimposable. If you place the hands like this, these two are different. They are not superimposable, but they are mirror images. Okay, got it? For enantiomers, you just remember your hands. Okay. So stereoisomers which are non-superimposable, but they are mirror images. They are usually represented by capital D and capital L. Okay. Now we will see this example. This is Fisher's uh, projection. We will discuss about Fisher's projection later. Now, if you see carefully, the OH group is in the right side of the penultimate carbon, and so it is D-glyceraldehyde, and the OH group is present on the left side, so it is L-glyceraldehyde. It is based on the OH group which is present in the on the penultimate carbon. Okay. Now we are going to discuss about diastereomers now. Diastereoisomers. Okay. Now, if enantiomers are mirror images, diastereomers are not mirror images. Simple. Stereoisomers, which are not mirror images to each other, they are called as diastereomers. In diastereomers, as we have seen earlier, it is of two things. One is your epimers, and another thing is your anomers. Okay. Now we'll see what is epimers. Diastereomers, note down, diastereomers are diastereoisomers that differ around the configuration of a single asymmetric carbon other than anomeric carbon. So these epimers are diastereomers that differ around the configuration of a single asymmetric carbon. We will see the example. Other than anomeric carbon. What is anomeric carbon in glucose? Yes, it is C1 carbon is the anomeric carbon. What is the anomeric carbon in fructose? Yes, it is C2 carbon. Okay. Now we'll draw the structure of glucose and mannose. Yeah. So this is the structure of glucose. Very good. Now we will draw the structure of mannose. Is glucose. Draw the structure of mannose. It's a 6 carbon compound, and this is your mannose. Okay. Now see this second carbon in glucose and in mannose. Apart from second carbon, rest of the structure is same. So if you see the definition of epimers, a single acid, this it differs in a single asymmetric carbon atom other than what, anomeric carbon. Okay. Now in the same way, what are C2 epimer of glucose is, yes, mannose. We are writing epimers of glucose. And C3 epimer of glucose is allose. C4 epimer is galactose. And C5 epimer is idose. Okay. You can remember with a mnemonic Maggie, MAGI. Write down the numbering 2, 3, 4, 5. Got it, students? C2 epimer is mannose, C3 epimer of glucose is allose, and C4 epimer of glucose is galactose, and C5 epimer of glucose is idose. Okay, clear? Okay. Now, it doesn't mean that mannose and galactose are epimers. Okay, glucose and mannose are epimers, and glucose and allose are epimers, but not mannose and allose, but not mannose and galactose. Got it? Okay. Now, conversion of one epimer into another is by the help of enzyme epimerases. Okay, UDP glucose is getting converted into UDP galactose with the help of what? Yes, UDP glucose 4 epimerases. Okay, got it? Very good. Now we will look into anomers. Now anomers can be seen only with the ring compounds or cyclic compounds. It can be seen only with ring structures. Okay. Now these anomers are formed, as the name implies. You can see anomers are formed around which carbon, students? Anomeric carbons. What is the anomeric carbon of glucose? Yes, C1 in glucose is anomeric carbon. And what is the anomeric carbon in fructose? Yes, C2 is the anomeric carbon of fructose. Okay. Now, usually these are represented as alpha and beta. Okay. I had drawn this diagram. Just see it carefully, students. See, this is Fisher projection, and these cyclic structures are called as Haworth. Haworth structures. Okay. Now, if you carefully see this structure, glucose, here it is getting converted into cyclic forms through an intermediate hemiacetal. This is hemiacetal. Okay. Now, how can you identify alpha or beta? I will tell you the mnemonic, students. See the position number 1. It is the anomeric carbon in glucose. It is C1. So in the C1, if OH group is on the top, it is beta. Okay. If OH group is on the top, it is beta structure. If OH group is on the bottom, If OH group is in the bottom, it is alpha. Okay. How will you remember alpha and beta, students? Is like beta, Bhagavan ऊपर है, so Bhagavan B ऊपर, above. Okay, so that is why I had drawn the structure of beta on the top and alpha on the bottom. Okay, got it, students? Fine. Now we will discuss about optical isomerism. Till now, is it clear? Okay. Optical isomerism. Few textbooks has given optical isomerism is a is one of the thing in stereoisomerism, and few have given it separately. Okay. Suppose if you have taken a solution of monosaccharides or carbohydrates and you pass a plain polarized light through it, if this light gets diverted to the right hand side, it is small d, and dextrorotatory, which is dextrorotatory, it is also represented as plus, and if it gets left side, it is small l, which is levorotatory, which is also represented as minus. Now glucose in a solution will cause plane polarized light to go plane polarized light to right side. That is why glucose is also called as dextrose. Okay. Now, what do you mean by racemic mixture? If at all equal amounts of D and L isomers are present in a solution, equal amounts, then the net optical rotation will be 0. That means there is no net optical rotation. Okay, there is no net optical rotation. Such a mixture is called as racemic mixture. Okay. Now, what is the use of it? If you are given a natural sugar and a synthetic one, natural and synthetic, natural sugars will show optical isomerism, they are optically active, and the synthetic ones are optically inactive, they are racemic. Okay, got it? Fine. Now we are going to discuss about muta rotation. Muta rotation means interconversion of anomers. See how are they interconverting? We are going to see it now. Usually crystalline glucose is in alpha D glucopyranose form with optical activity of plus 112 degrees. Okay. Now, whenever you dissolve it in water, this alpha thing will loses its cyclic thing to form a linear, and it is again converted into, beta form, beta d glucopyranose, which is having an optical activity of plus 18.7 degrees. Okay. So after that, finally it will reach one equilibrium state. After the final equilibrium, in that solution, it is almost 36 percentage of alpha and 64 percentage of beta. Okay. So this spontaneous conversion of beta into alpha, sorry, the spontaneous conversion of alpha into beta form, it is called mutarotation. Okay. In a solution, this spontaneous conversion of interconversion of sugars in a solution, or the spontaneous interconversion, is known as mutarotation. Okay. This mutarotation is accelerated by acids and bases, and this mutarotation is prevented when anomeric carbons are involved in the bonding. Okay. During glycosidic bond formation by anomeric carbons. Got it, students? So this is all about your monosaccharides and isomerism. Okay. Thank you.